So our apparatus starts off with an inclined plane. This inclined plane has the marble go straight down into a cup. That cup is the right side of our pulley, and as the cup goes down, the lever is raised. The marble that is on top of that lever is released and goes onto another inclined plane. That inclined plane is followed by an inclined plane and then a screw. At the end of the screw, the marble goes through a series of 3 more inclined planes. And then finally it goes through a tube, and then at the bottom of that tube we have our final lever, which our flag is connected to. When our lever goes down, our flag is raised to 22 centimeters. So our marble starts over here, and as it rolls down this inclined plane, it shows kinetic energy. Over here, right before it enters the cup, the marble transfers this energy from kinetic to potential because it is suspended with a ZRL. And then, as it enters the cup, it changes that potential energy into kinetic energy again. Let's hope that's okay. So, when this marble enters the cup, it transfers its kinetic energy into this cup, acting on the pulley, which causes this lever to go up. This marble here has potential energy, and when this pulley is pulled with the energy from the first marble, it has kinetic energy because it transfers its potential energy into kinetic when this lever raises and the marble goes.
So for number 2, it was calculate how much gravitational potential energy the apparatus begins with. In other words, how much energy do you give to the apparatus when you first drop the marble in? Use your flag's resting position as a 0. So to find how much gravitational potential energy the apparatus needed to begin with, we have to use the equation UG equals mass times the force of gravity, which is defined as 9.8 meters per second squared, and that how high the object is within our apparatus. So for ours, our marble was about 5 grams, so when converted to kilograms would be 0.005 kilograms times 9.8 times 0.68 meters. So how we got the height was we measured the lowest point, which will be the tip of the flag, lowest tip of the flag, and we measured up to the top of our apparatus, which we will get about 0.68 meters. So when doing all the calculations, it will end up being about 0.033 joules, which would be how much energy it needed for us to lift the marble and to place it on top of the apparatus. So for number 3, it was calculate the speed at which the flag is raised using speed equals distance the flag travels divided by the time it takes the flag to go this distance. So by measuring the distance the flag had to travel, we would use the lowest point of the flag, and we would run the apparatus and we would measure how high the flag is raised. So when measuring that, we had about 22 centimeters, so we would convert that to meters. So that would be about 0.22 meters. And we recorded three trials of our apparatus, and we would average out the 3 trials to get around 0.39 seconds. So when doing the calculations, it will be speed equals distance over time, which we plugged in 0.22 divided by 0.39 to get around 0.56 meters per second. The reason why we had to use 0.22 was because that was the original ZRL, and we had to raise the flag, and that was the distance from the ZRL to the tip point.
My name is Adrian Jaworski, and my first question is, was energy conserved from the initial potential energy of the apparatus by the marble to the final kinetic energy of the flag? The answer is yes and no. Yes, because the law of conservation of energy states that energy is neither created nor destroyed, therefore energy had to go somewhere. And no, because energy is lost in multiple forms throughout the apparatus. The first form is energy is lost in sound. The sound is created by the marble rolling down the apparatus. the second way energy is lost is due to friction. For instance, the lever that the second marble sits on before that the pulley pushes over, it has a nail, and that nail flips, or the nail turns, creating friction, which is how the apparatus loses energy. Second of all, the flag also has a nail inside of it because it's another lever, and it also loses energy throughout that nail due to friction. Once at the bottom also, the marble loses potential energy because it's at the bottom of the apparatus, and also its kinetic energy is transferred into the flag, which is why the flag moves. But the kinetic energy of the flag moving is different than the potential energy, because if you were to add up the potential energy, if you were to add up the kinetic energy of the flag moving and the energy of the sound that the marble created and the friction that the marble has created, that would equal up to the potential energy of 0.033 joules. The question is, explain whether or not you can turn your apparatus into a perpetual motion machine. Explain how if yes, explain why not if no. Our answer is no, because energy is lost through friction, which is created by marble rolling down the machines, and then also energy is lost through sound because the marble is rolling down the machine. Another thing would the marble would also have to create sufficient energy need sufficient energy to restart the whole process of bringing the marble back up to the top, to restart the system, the apparatus. And the marble would not have, at some point, would lose all its energy to friction and sound and raising the flag.